Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine standing on the jagged shoreline of an alien world, a world where the air is thick with haze and the scent of hydrocarbons drifts on a bone-chilling breeze. The ocean before you isn't blue. It's a dark, shimmering bronze, more viscous than water, lapping in syrupy waves beneath a dim, rust-colored sun. Lightning flickers in the distance, illuminating clouds not of water vapor but methane gas. You take a step closer. The waves slosh gently against the rocks, but it isn't Earth you're standing on. This is HD 102956b, an exoplanet more than 200 light-years from home, and it might just be the most important place we've ever found in the search for life beyond Earth. For decades, we've followed a simple rule in our cosmic search. Look for water, and you might find life. It's a philosophy born of experience. Earth's biosphere, from coral reefs to mountain peaks, is drenched in water, and our biology is tailored to it. Water is a powerful solvent, a thermal regulator, and the foundation of cell membranes and DNA. But what if our water obsession has blinded us to stranger possibilities? What if life doesn't need water at all? That's where this incredible discovery comes in. A team of astronomers from the European Southern Observatory, collaborating with researchers using the JWST, the James Webb Space Telescope, made headlines around the world when they detected unusual spectral signatures on HD 102956b. Initially thought to be noise or misreadings, repeated observations revealed consistent infrared absorption patterns. These patterns matched not just methane gas, but reflections consistent with large, stable bodies of liquid methane on the planet's surface, potentially oceans spanning hundreds or even thousands of kilometers. Now, methane as a liquid only exists under extremely cold conditions. To stay in a stable liquid state, the temperature must be below -161 degrees Celsius. HD 102956b is a cold world orbiting a small, cool K-type star. Its distance from its star places it within a different kind of habitable zone, a cold zone where methane, not water, defines the ecosystem. The planet's surface is estimated to sit around -140 degrees Celsius, perfect for methane oceans to form and persist. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. The existence of stable liquid methane on a planetary surface is rare, but not entirely unknown. Titan, Saturn's largest moon, has methane lakes, rivers, and even methane rainstorms. NASA's Cassini-Huygens mission captured radar images of enormous seas on Titan's North Pole, with wave patterns hinting at surface winds. But Titan is small and cold, with a thick nitrogen atmosphere and limited solar radiation. HD 102956b, in contrast, is a full-fledged exoplanet, larger, more massive, and potentially far more geologically active. The JWST made its methane detection during planetary transits, when HD 102956b passed in front of its star from our viewpoint. During these events, starlight filters through the planet's atmosphere, and the gases there absorb certain wavelengths. By studying the absorption lines, scientists can determine which molecules are present. Methane's signature is distinct, but what truly astonished the team were the spectral shifts indicating liquid methane, reflections and refractions consistent with calm, glossy surfaces. This required modeling that accounted for atmospheric scattering, cloud formation, and surface reflectivity. What they found was stunning. These weren't methane clouds or mist, they were oceans. But oceans alone don't make a world alive. So, could something actually live there? Astrobiologists have long speculated on life as we don't know it. On Earth, all life shares the same biochemistry: DNA, proteins, water-based metabolism, but some scientists argue this may not be the only way. In 2015, researchers at Cornell proposed the idea of methane-based life. They coined the term azotosomes to describe hypothetical cell membranes stable in liquid methane. Unlike Earth's phospholipid bilayers, which require water, these azotosomes could form from nitrogen-rich molecules like acrylonitrile, already detected in Titan's atmosphere. Imagine that for a moment, cells floating not in oceans of water, but in seas of methane. These organisms might be slow, their metabolisms crawling along due to the low temperatures, but they'd be alive. They might not breathe oxygen, but hydrogen. They wouldn't release carbon dioxide, but perhaps exhale exotic byproducts like acetylene. They'd look nothing like us. No flesh, no blood, no eyes. Maybe they'd resemble blobs or film, or perhaps they'd evolve into sophisticated, intelligent forms completely unlike anything we can comprehend, and HD 10295 6b could be their cradle. To further investigate, scientists plan to measure the planet's atmospheric composition over time, looking for imbalances, anomalies in gas ratios that could suggest biological activity. On Earth, methane and oxygen are both unstable. Without life, they'd quickly react and disappear. Their constant presence in our atmosphere is a sign of ongoing biological processes. So if we detect unusual levels of compounds like hydrogen, cyanide, ethane, or nitrile is on HD 10295 it could point to something incredible: methane-based life at work. Consider the implications. If methane-based life exists, our definition of a habitable world expands dramatically. Suddenly dozens, maybe hundreds, of cold exoplanets once deemed uninhabitable could be bursting with life. Life that evolved differently, life that rewrites biology. Think of the stories those civilizations might tell if they exist. They would look up at a distant blue star, our sun, and wonder if anything lives in its warm glow. And now we look at their pale frozen world and wonder the same. The methane seas of HD 10295 are more than a scientific curiosity. They're a cosmic invitation, beckoning us to shed our earthbound assumptions and open our minds to stranger possibilities. Oceans don't have to be blue, life doesn't have to breathe air, and the universe doesn't have to follow our rules. To truly understand the weight of this discovery, we need to shift perspective, not just from Earth to an alien world, but from what we think life must be to what it could be. Because as we stare across the methane waves of HD 10295 we're forced to ask, is life tied to Earth's formula, or is it something more universal? Something that adapts to any chemistry, any condition? That question, believe it or not, has been haunting scientists for over a century. In the late 1800s, before DNA had even been discovered, the idea of vitalism, that life required some kind of mystical essence, was already dying. Chemists were starting to understand that living matter was just chemistry. Complex, yes, but governed by the same rules that shaped stars and minerals. Fast forward to the mid-20th century, and biologists like Carl Sagan and Lynn Margulis began seriously entertaining the idea that life might exist elsewhere, not just in our solar system, but far beyond. But they all shared one assumption: wherever life exists, it probably needs liquid water. That assumption was grounded in logic. Water is abundant, polar, and remains liquid across a fairly wide temperature range. It's excellent at dissolving salts and organic molecules, allowing the chemical reactions of life to take place. On Earth, every living thing relies on it. No exceptions, and yet Titan challenged that logic. In 2005, when the Huygens probe descended through Titan's smoggy skies and landed with a crunch on its frozen surface, it sent back images that shocked the world. Riverbeds carved by liquid, pebbles shaped by erosion, mist and drizzle. And yet this wasn't water. It was methane and ethane, flowing like water at minus 179 degrees Celsius. A complete hydrological cycle. Without water, that moment changed everything. Suddenly, astrobiologists began to whisper the unthinkable. Could life adapt not just to a different environment, but to a different solvent entirely? Enter the groundbreaking paper from Cornell University in 2015. A team of chemical engineers led by Dr. Paulette Clancy and Dr. James Stevenson simulated how a methane-based membrane might behave. They used computer models to test how molecules like acrylonitrile could form flexible, stable membranes in cryogenic methane. These weren't mere theories, they were molecular structures built and tested virtually, showing lifelike behavior. The result? Azotosomes, the alien equivalent of a cell wall, capable of enclosing organic molecules and maintaining structure, just like our cells do in water. And here's the twist. Acrylonitrile wasn't just theoretical. It had already been detected in Titan's atmosphere by the ALMA radio telescope and the Cassini spacecraft. This molecule, toxic and volatile on Earth, might form the basis of life in methane oceans. Not in the distant reaches of science, fiction, but possibly right now on Titan and now, maybe on HD 102956b. Let's paint a picture. Imagine a thick layer of hazy clouds swirling high above the methane oceans. Occasional rays of orange-tinted sunlight break through the haze, glinting off viscous, dark seas. Beneath those waves, tiny structures float, azotosomes, organic droplets, strange chains of hydrocarbons. Over time, those structures interact. They absorb, they split, they replicate, not with DNA, but with some alien alternative. Evolution begins just as it did on Earth, only colder, slower, and infinitely stranger. It might take millions, perhaps billions of years, but eventually complex structures emerge. Maybe even organisms, maybe colonies, maybe intelligence. We don't know what methane-based life would look like. It might not be carbon black and tentacled like something from science fiction. It might be transparent, or reflective, or even bioluminescent. It might move by altering its density, sinking and rising in the methane depths. It might communicate chemically, or through vibrations in the liquid, or perhaps even electromagnetically. And that brings us back to HD 102956b. The key to identifying life there won't be spotting a creature through a telescope. That's far beyond our current capabilities. Instead, scientists are looking for what they call biosignatures, chemical fingerprints that are hard to explain by non-living processes. For example, if a planet has stable levels of hydrogen and methane coexisting in the atmosphere, it might suggest life is constantly replenishing those gases. On Earth, oxygen and methane coexist only because life maintains them. Left alone, they would react and cancel each other out. So if we observe similar chemical tensions on HD 102956b, gases that shouldn't persist together unless something is maintaining them, it could be a smoking gun. And that's where the JWST comes in again. With its ability to observe in the mid-infrared spectrum, the James Webb Space Telescope allows astronomers to detect molecules like methane, ethane, hydrogen, carbon monoxide, and more. Early data from HD 102956b already suggest atmospheric imbalances. Some measurements hint at a disproportionate ratio of methane to hydrogen, possibly indicating ongoing chemical activity. But here's the catch. It's not conclusive. Abiotic processes like photochemistry driven by starlight or geothermal reactions from the planet's interior could also explain these imbalances. That's the frustrating beauty of astrobiology. We can't just knock on the door and ask if someone's home. We have to decipher a world's secrets from across the abyss of space using only light. Yet, something feels different this time. The intensity of the methane reflection, the consistency of the liquid mapping, the anomalous gas ratios, even the planet's stable temperature profile, unusually steady for a world so far from its star, suggests something more than mere geology at work. Maybe it's life. Maybe it's not. But the mere possibility has lit a fire under the scientific community. Proposals are already being drafted for next-generation missions to study cold worlds more closely. Ideas for probes that could survive cryogenic temperatures, swim in methane, or even hover in dense alien atmospheres are being sketched. Some researchers envision Titan as a training ground, a place to test the technology before venturing to distant exoplanets like HD 102956b. Because here's the truth, discovering methane oceans was once unthinkable. Now, it's a reality. And if that's possible, what else might we find? Imagine standing on the surface of an alien moon orbiting HD 102956b. The sky above is a deep, oily black, not because it's night, but because light barely filters through the thick layers of hydrocarbon haze. The stars. Overhead are faint pinpricks, dwarfed by the looming red-orange glow of the planet itself. Under your boots, if you could wear any without instantly freezing solid, the surface crunches like snow, but it isn't snow. It's frozen methane, compacted by centuries of cryogenic drizzle. The air? So cold it could liquefy oxygen. And yet, something stirs beneath the ice. This might sound like science fiction, but scientists aren't ruling it out. To understand why, we need to dive into the physics and chemistry of methane-based worlds. Methane, a simple molecule made of one carbon atom bonded to 4 hydrogen atoms, behaves very differently in cryogenic conditions. On Earth, methane is a gas at room temperature, but on frigid planets and moons, where temperatures hover near -180 degrees Celsius, it becomes a liquid. It can rain from the sky, carve rivers, form lakes, and even create oceanic tides, especially if the planet has a strong gravitational pull from nearby moons or a parent star. Now consider this. Earth's oceans are dynamic systems. Currents carry heat and nutrients. Tides mix shallow and deep waters. This movement is essential for life, helping distribute energy and catalyze chemical interactions. For years, astrobiologists assumed that methane seas would be too sluggish, too still, to support anything complex. But new climate simulations from planetary scientists at UC Santa Cruz suggest otherwise. Their model, built on top of Titan's data and extrapolated for larger planets like HD 102956b, showed that methane oceans can indeed support convection currents, particularly when the planet has geothermal activity. In simpler terms, if HD 102956b has volcanic or tectonic processes beneath its crust, it could generate enough heat to drive thermal upwelling. That means the oceans wouldn't be dead and still. They could churn, mix, and evolve. And here's where things get even more fascinating. Geological activity not only stirs the oceans, it also provides key ingredients for life. On Earth, deep-sea hydrothermal vents teem with organisms that live entirely without sunlight. These life forms feed off the minerals and gases spewed from the Earth's crust, primarily hydrogen sulfide, methane, and ammonia. If HD 102956b has similar geothermal features, it could mean entire ecosystems exist beneath the methane surface, completely invisible to our telescopes, but potentially teeming with alien biology. These hypothetical organisms wouldn't rely on photosynthesis. They might use chemosynthesis instead, breaking down exotic molecules for energy. Their metabolisms could be based on silicon or even arsenic, elements that would be toxic to us, but might work just fine in their cryogenic chemistry. In a world where metabolism happens hundreds of times slower than ours due to the cold, life might evolve on geological timescales. Generations could span centuries. Communication could happen through slow waves of bioluminescent pulses, echoed across the liquid dark. But could we ever detect that life? The short answer is, not yet. But there are clues we can look for from afar, and scientists are getting better at finding them. The JWST, with its sensitive infrared spectrometers, can analyze the chemical composition of exoplanet atmospheres during transits. That is, when a planet passes in front of its star. As the star's light filters through the planet's atmosphere, specific wavelengths get absorbed by different gases. It's like reading the barcode of a planet's sky. On HD 102956b, this barcode revealed methane. No surprise, but also trace amounts of ethane, hydrogen, and something unexpected. Complex organic aerosols. These aerosols are tiny suspended particles made from long-chain hydrocarbons. On Earth, similar compounds form as pollution from burning fossil fuels. On Titan, they naturally occur as sunlight breaks down methane in the upper atmosphere, triggering complex chemical reactions. But on HD 102956b, the presence of such high concentrations of these compounds, at altitudes and densities inconsistent with purely photochemical models, has scientists scratching their heads. One theory, proposed in a recent paper from the European Southern Observatory, suggests that the concentration of organic aerosols could be maintained by a biological process, not unlike how Earth's plankton affect cloud formation and oxygen levels. If life exists in the methane oceans or upper atmosphere, it might be releasing these molecules as waste or even as communication signals. Think about that. We could be observing the planetary equivalent of a biosphere's exhale. Of course, there's always a skeptic's voice in the room, and rightly so. Planetary scientists caution that non-biological chemistry can mimic life's signatures. For example, volcanoes and lightning can produce organic molecules in abundance. Ultraviolet radiation can drive complex reactions in the absence of biology. That's why the scientific community insists on multiple lines of evidence before jumping to conclusions. But even cautious scientists admit, this planet checks more boxes than most. It's got liquid seas, it's got a thick, stable atmosphere, it's got thermal variation and cloud dynamics, it shows signs of complex molecules, and, perhaps most intriguingly, it's unlike any other exoplanet we've studied so far. One particularly stunning revelation came just weeks ago from a new data analysis using AI models trained on thousands of known exoplanet spectra. When applied to HD 102956b, the algorithm flagged an anomaly, a recurring narrowband infrared emission spike centered around 3.1 microns, a wavelength often associated with symmetrical CH stretching in organic compounds. It's not definitive, but it's unusual. And more importantly, it's repeating. Every time the planet transits, that spike appears. If it were just noise, it would be random. But it's not. What could cause a consistent spectral spike at a frequency linked to organics? Some researchers speculate it might be a form of molecular fluorescence, energy absorbed by alien molecules, and then re-emitted in a predictable way. Others whisper wilder ideas. Could it be an artificial signature? A signal? A beacon? Probably. Not, but the fact that we're even asking shows how far this discovery has pushed the boundaries of our thinking. We're no longer just looking for water and Earth clones. We're exploring planets where the oceans are methane, the air is toxic to us, and yet the potential for life might be greater than on any rocky world, and with each passing observation, the mystery deepens. As we venture deeper into this cosmic mystery, it becomes clear that the discovery of a methane ocean world like HD 102956b isn't just a scientific breakthrough, it's a philosophical revolution. For centuries, we've framed the search for life around the idea that water is essential. It's been our guiding star, our belief that life must be just like us. Biochemistry bound by the familiar rules of our earthly environment. But what if this is all wrong? What if the universe doesn't play by the same rules? What if, instead of life looking like the creatures from Avatar or the tiny glimmering microorganisms of Earth's oceans, life could look entirely different? And not just one kind of life, but myriad forms of it, evolving in places we never thought to look, beneath the icy methane seas of a distant exoplanet. Consider the implications of this discovery. We're not talking about life that could be similar to the microbes we find under Earth's oceans or deep beneath the Antarctic ice. No, HD 102956b might harbor a fundamentally different kind of biology, one that has evolved in a solvent that isn't water, one that uses the cold, thick methane as a medium for life processes, relying on chemistry that seems foreign to us, yet might be perfectly viable in the harsh, cryogenic depths of the alien ocean. And this might not be the only world out there like this. Astrobiologists now know that the number of planets in the habitable zone of their stars, where liquid water could exist, might be vastly overestimated. Research from the past decade suggests that exoplanets in the cold zone, where temperatures drop low enough for methane to exist as a liquid, could host forms of life entirely unrelated to what we know. These zones, previously thought inhospitable, could harbor rich ecosystems in ways that challenge our assumptions. And it gets even more interesting. Scientists have begun to ask, if life can exist in methane oceans, could it adapt to other environments with different solvents altogether? Could ammonia, found in large quantities on moons like Triton, serve as a solvent for life? Or what about formamide, a molecule similar to water, but with an even lower freezing point found in comets. These solvents are all chemically capable of supporting life, just as water does. It's just that they would require organisms to use completely different biochemistry. Imagine an alien world covered by a thick atmosphere of ammonia and formamide, with a sky so dense that sunlight struggles to penetrate. The surface might be dotted with thick clouds of toxic gases, swirling violently due to the extreme temperature shifts between day and night. Yet below the surface, a bustling ecosystem might exist, thriving in ammonia lakes or beneath a frozen shell of formamide ice. Creatures here wouldn't breathe oxygen or even use carbon in the same way we do. Instead, their chemistry could be based on silicon or other metals, using ammonia's unique properties to build the complex molecular structures needed for life. It's a far cry from the lush blue planet we call home, but it could be a world rich with life just waiting to be discovered. And that brings us to one of the most mind-bending questions of all. What if these alien life forms are more advanced than we are? Think about it. Earth life is based on a certain set of rules: our carbon-based biochemistry, our reliance on water, our dependency on oxygen to fuel the energy needs of our cells. But that's only one pathway in the vast possible chemistry of life. What if a civilization evolved in a methane ocean world, or one that uses ammonia as a solvent? Their biology would be completely alien to us, possibly so different that we wouldn't even recognize it as life. Their technology, too, could be unlike anything we've ever imagined. Perhaps their machines don't run on electricity, but on chemical processes we can't yet fathom. And if such civilizations are out there, what if they are watching us right now? The search for extraterrestrial intelligence, SETI, has primarily focused on searching for signals that match our own technological patterns, radio waves, light pulses, or electromagnetic emissions. But what if advanced civilizations in these methane or ammonia-based worlds are operating on a completely different frequency? What if their communication methods don't rely on electromagnetic signals at all? Could they use chemical signals, or perhaps vibrations in their thick atmospheres, as a means of transmitting information across vast distances? Or perhaps their technology is so advanced it no longer relies on traditional communication at all, existing in ways we can't yet comprehend. If that's the case, it could mean that all along we've been listening for the wrong things. Instead of trying to detect signals from worlds that are just like us, we need to think beyond our own limitations and consider how life and intelligence might express itself in environments totally alien to our understanding. And it doesn't stop there. There's another equally mind-blowing possibility we have to consider. In our quest for alien life, we've always thought that we were looking for other life forms, beings who evolved from the same building blocks that we did. But what if the truth is far stranger? What if, in a universe as vast as this one, life isn't just rare, it's diverse, a kaleidoscope of different unimaginable forms? What if in places like HD 102956b, methane-based organisms have evolved not just to survive, but to thrive in ways we cannot even begin to comprehend? That thought is both terrifying and exhilarating. It forces us to expand the boundaries of life and intelligence, to consider a universe where the rules are different, but the potential for discovery is limitless. Every new world like HD 102956b is a testament to how little we truly know. Each discovery shatters old assumptions and opens the door to new possibilities, some of which might be stranger and more wondrous than we ever imagined. As we stand on the precipice of this discovery, one thing is clear: the universe is far more mysterious, far more complex, and far more alive than we could ever have guessed. And the more we learn about exoplanets like HD 102956b, the more we realize that our understanding of life is just beginning. As we reach the end of this mind-bending journey, the enormity of what we've just explored starts to settle in. What we've learned is more than just about a distant exoplanet. It's a gateway to rethinking everything we thought we knew about life, the universe, and our place within it. Imagine, just for a moment, that the next great discovery doesn't involve finding a planet just like Earth. Instead, It involves the discovery of life not only in places we least expected, but in forms we can't even comprehend. Picture a civilization thriving in methane oceans, communicating through chemical signals, using ammonia instead of water. Their reality is so foreign to us that we might not even recognize it as life. And yet, they exist, just beyond the horizon of our current understanding, waiting to be discovered. What if that world, HD 102956b, represents just the beginning? If life can exist in methane oceans, if complex carbon-based biochemistry isn't the only path to life, then the possibilities expand exponentially. Could there be other worlds where life thrives in environments even more alien to us? Worlds with oceans of ammonia, atmospheres rich in hydrogen, and skies teeming with lightning storms more violent than anything we could imagine? Worlds where life is based on silicon, not carbon, where intelligence evolves in ways we can't predict, and technology operates in forms we can't yet dream of. We're standing on the edge of an intellectual and philosophical revolution, one that asks us to think not just about what's out there, but also about what it means to be alive in the first place. As we gaze at these distant planets, it becomes clear. The search for extraterrestrial life is no longer about searching for ourselves. It's about expanding the definition of life, exploring the diversity of what life could be. And perhaps most thrilling of all is this: the universe is far more vast and mysterious than we ever imagined. With each new discovery, like that of HD 102956b, we peel back the layers of the unknown, revealing that there are infinite worlds out there, each with its own story, its own mysteries, and its own potential for life. But the questions don't stop there. If life can evolve in methane seas on distant exoplanets, then what does this mean for our understanding of the origins of life here on Earth? Could life have started differently than we thought? Could it have begun in extreme environments like the ones we're now discovering on these distant worlds, only to evolve into the familiar forms we see today? The implications are mind-blowing. Imagine just for a second the possibility that we are not the end of the line, but the beginning of something far greater. That somewhere, beyond the vast stretches of space, are civilizations far more advanced than our own. Civilizations that have long ago learned to harness the strange chemistry of their worlds, perhaps even harnessing the very elements that we are just beginning to understand. In that vast, uncharted expanse, are we alone? The answer, for now, is uncertain. But with every new discovery, we inch closer to understanding that we may not be alone at all, and the search for life has just begun. So what's next for us? How do we continue this journey? The tools of science are only getting better, and with each new breakthrough, from the incredible observations of the JWST to the development of advanced AI models that help us decipher alien atmospheres, we are closer than ever to uncovering the secrets of the universe. But none of this would be possible without the people who dare to ask the big questions, who push the boundaries of what we know, and who dream of a future where humanity has its place among the stars. The discovery of HD 102956b is just the first step on a journey that will span centuries. And you, yes, you, are part of that journey, whether you realize it or not. Every time you ask questions, every time you engage, with discoveries like this, you're helping shape the future of exploration. The universe is vast. It is full of mysteries waiting to be unraveled. And just like the explorers of old, it's up to us to take the next step into the unknown. So let me ask you this. If we are truly on the verge of discovering life in places we never expected, what does that mean for our future? What does it mean for the way we think about our own existence? Are we ready to meet the unknown? Are we ready to embrace the strange, the different, the alien? If you've enjoyed this journey into the unknown, there's so much more to discover. So join me as we continue to explore the mysteries of the universe together. Don't forget to like, share, and subscribe, because the adventure is just beginning. Leave your thoughts, your questions, your theories in the comments below. Who knows? The next great discovery might just be one of your ideas. Thank you for being part of this cosmic exploration. Until next time, keep looking up. The universe is waiting.